We are looking today at related rates and how they relate with the implicit differentiation that we have been doing. These are just going to be problems with two or more variables, but now instead of going, dy dx, we're doing both variables with respect to a third variable, with respect to time. So this is what we are going to be doing. Here's an example. Suppose both x and y are differentiable, and we have this function, y equals x squared plus 3. We're going to take a derivative just like we've done before. So the derivative of y is just 1, but now we're going to say it's with respect to t, so it's dy dt. Same on the right-hand side, derivative of x squared is 2x, but it's with respect to t, so dx dt, and then the plus 3 stays on its own. What they want us to do is find what dy dt is, but at a certain point. So in this case, when x equals 1. So we're going to plug in that x equals 1, and also that at this point, dx dt equals 2. So all we're going to do is just plug in those values. So 2 times 1 times 2, which means at this point, dy dt is equal to 4. That's the way you do these. You do the derivative and then just plug in what you know. Same thing here. We're going to make it 8x. This will be dx dt because I took a derivative of x with respect to t. Second one is going to be 10y dy dt. And the derivative of 36 is 0. Same thing, plug in what we know. Well, x is 2 and y is 2. So I'm going to say 8 times 2 and dx dt is 7. Plus, this will be 10 times 2 dy dt equals 0. We need to get dy dt by itself, just like it was any variable that we've done before. So this number here is going to be whatever 16 times 7 is, which, as you can tell, I don't really know. 16 times 7 is 42, so 112. 112 plus 20 dy dt equals 0. That means that dy dt will equal negative 112 divided by 20. That's all you really have to do, is they'll want it at a specific point, and they will tell you what the differential is. Now, another thing that we're going to, beyond that, is when we start doing the word problems. And these are the steps that you'll want to use. Essentially, just set up the problem, see what you know, and plug in for what you don't know. So, air is being pumped into a balloon at this specific rate. Find the rate of change of the radius. Well, the rate of change of the radius, we're talking about air being pumped in, so we've got to talk about volume. Volume of a sphere, which is 4/3 pi r cubed. Okay? We're going to do a derivative with respect to time. So, dv dt is going to equal, when I bring that 3 down in front of the whole thing, I'll now have 4 times pi r squared, but dr dt, because we had it with respect to t. Same thing now, plug in what we know. This is the rate that the volume is being changed. So that's dv dt. That's our rate of change. Equals 4 times pi. The radius is 2 inches at this point, so 2 squared, and dr dt. All we need to do from here, solve for dr dt. So we're going to have 4.5 divided by, that'll become 16 pi down here, is equal to dr dt. And you could go ahead and plug into your calculator and get the exact value, or an estimated value, but that exact value is more than fine for us. Okay? One other example, just for setting it up. We're going too far. The side of a square increasing at the rate of 10 feet per minute. How fast is the area changing when the sides are 15 feet long? So, we're going to say the area. We're looking at area in the end. You want to know how fast area is changing. Area of a square is just going to be its side length squared. That means dA dt, the derivative of area, is going to be 2s dx dt. Okay? Again, what do we know? Well, we want to know how fast is the area changing. We want to know dA dt. What does it equal? We know that the sides here are 15 feet long, and the side of a square is increasing at 10 feet per minute. It means that the change in s, the change in the side length, is changing at 10 per minute. So those are what we are going to plug in. We want to leave dA dt, we don't know what it is. 2 times the side length is 15 and DSCT is 10. That means that we have 20 times 15 for 300. And our units then would be the ADP. Well, what is area here? If we're talking in feet, we're going to have feet squared per minute as our unit. Those are the basic ones. Later we'll get on into using two variables and how we can kind of compare them. But for right now, this is what we want to be able to set up and solve with these word problems and with these related rates.